test markers.
No.
There's a bunch of little light and color things in the back that are fun to play with. So I'll grab those. And the seats are continually moving forward for reasons that no one knows.
I have not used this.
Mr. Byers, are you on TikTok?
No, I don't do TikTok. I don't tick. I don't talk. I don't gram. I don't tweet. I did Facebook for a while because no joke. A student said about 10 years ago, Mr. Byers, you should get on Facebook.
Are you serious?
I'm like, why?
Yeah,
So you can. I can remember what he said. So I got on Facebook and that lasted a couple of years. And
No social
Mr.
media.
Schultz made a TikTok today.
He
He
did?
didn't want to. He got duped into it.
you got duped into making a TikTok?
I didn't even know
Is there a
that
name
you
for
were
that?
making a TikTok.
You're a faux TikTok.
I don't know.
Okay, well, speaking of TikTok, so the last unit we're doing is light and quantum, and it's interesting. So it's going to start pretty simple to talk about light and light waves, and then we're going to talk about where light comes from in the atom. And here's a little preview. Light comes from atoms when electrons jump up to higher energy levels and then come back down. So if you remember from your chemistry from last year, it's like, who remembers chemistry from last year? If you remember chemistry from last year, you got a nucleus in the, we're chilling out with some protons. You got some protons, and around the nucleus you have electrons, and the electrons are in levels. An electron can jump up when it absorbs energy, and it gets a little star, and it's like, I got a bunch of energy. And then it can jump back down. And how fast it jumps up and down, and the energy levels from which it jumps up and down determines the amount of energy that's given off. So just like a sound wave is a vibration in air, where you're like, and molecules bang, 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 up to you, a light wave is a vibration in an electric field that is created by electrons bouncing or jumping up and jumping down between energy levels. Okay, so that's quantum, and it's called quantum. Remember, if you watch the video, you learned about this. It's called quantum because quantum, remember from chemistry, means a set size. A single quanta is a set packet of energy of a specific size. Okay? It's kind of like a penny. A penny is a quanta of money. $3 is quantum of money. So the smallest unit of money we have, as far as you know, is a penny. That is the quanta of American money. Okay, if you are in Japan, a yen is the smallest quanta of Japanese money, as far as you know. So when you have a whole bunch of them, it's quantum. Okay? And when electrons jump from one level to another level and then come back down, they require that quanta of energy, and they give off that quanta when they come back down. Now, one thing that you do need to realize is there's this thing called the electron volt, and it's based upon the fundamental charge of an electron. The fundamental charge of an electron is 1.6 times 10 to the negative 19 coulombs. Remember, charge is coulombs. Okay? So the fundamental charge of a single electron is negative 1.6 times 10 to the negative 19 coulombs. Now, if that charge of one fundamental electron, we'll call it E, passes through 1 volt, it takes or gives off, depending on if it's going uphill or downhill. If it's going from a high potential to a low potential, it's going to give off this number of joules. If we're driving it to a high potential, it's going to require that amount of joules. So a single electron traveling through 1 volt is going to require or give off 1.6 times 10 to the negative 19 joules. In other words, 1 coulomb traveling through 1 volt will require or give off 1 joule. So 1 electron traveling through 1 volt will give off or take in 1 electron volt. I'll say that again. It's kind of complicated. I went really fast. An electron has the smallest quanta of charge that exists. It is called the fundamental charge, and that is negative 1.6 times 10 to the negative 19 coulombs. When that electron is forced to travel through a voltage, it is going to give off energy if it's going through a thermodynamically favored system, or require energy if it's traveling through a thermodynamically unfavored system. So right now, your cell phones all run on 3.7 volts. And what that means is, every time there's a tiny chemical reaction going on in our phones, so everybody's got them. If you take your phone apart, you can actually find a lithium-ion battery, but they're all based on 3.7 volts. So the chemical reaction that's going on inside your phone, there are electrons that are traveling through 3.7 volts and producing 3.7 joules of energy, which can be used to keep your phone or keep your computer on, or turn your screen on, or make your phone vibrate, or make the audio work, or something. So that's what we're talking about. Electrons have a fundamental charge, and when they travel through a potential, they will require energy in the form of joules if we're forcing them to do something that is not thermodynamically favored, or they will release an amount of energy if we're doing something that is thermodynamically favored. Okay. How's that for complicated? We're good? What questions do you have?
So up equals require, down equals release?
Yes. So if you are forcing something to become higher in potential, remember, we and the universe like to be in a low potential state. You want to watch TV standing up or laying down?
Laying down.
Yeah. I want to be in a low potential state because I'm a victim of the universe.
Absolutely. Wow.
All right. Now, okay, so there we go. We're eventually going to get to this point where we talk about waves, and if you watch the videos, you know about this. We're going to talk about waves and particles. We're going to talk about light behaving as both a wave and a particle. It's called wave-particle duality, and that's the end of quantum. All right, so when you look at all the electromagnetic spectrum, and it's called the electromagnetic spectrum because the thing that is vibrating are electric fields, and those also produce magnetic fields. So the electromagnetic spectrum can be chopped into little bits. This poster's also right there. Came from the Advanced Light Source in Berkeley. Used to be one of the first linear accelerators, or synchrotrons. I don't remember if it's a circle or a straight line. Anyway, one of the first atom smashers that was built back in the 50s. And so we split up our electromagnetic spectrum into long radio waves. Things that have long wavelengths have small frequencies. Remember frequency?
Mm-hmm.
Wavelength from our study of waves. So things that have long wavelengths have small frequencies. Things that have high frequencies have itty bitty wavelengths. What's the important thing about light waves? They all travel at the same speed. They travel at the speed of light, which is 3 × 10⁸ meters per second in a vacuum. 2.98 in air, so we just rounded up to 3. Okay, so the speed of light, just like the speed of waves, we've been doing before, we did waves equals lambda f, is equal to the wavelength times the frequency. The good news is when we're talking about light, the speed's always the same. When the speed isn't the same, that's the realm of optics, and we're probably not going to get into geometric optics. That's how lenses work. And then the energy of a wave or a photon of light is equal to hf. H is Planck's constant, and it's a crazy small constant. I'm going to come up to it again, but it's 6.63 × 10⁻⁴ joule seconds, -34 joule seconds. It's a tiny, tiny, tiny amount. So basically what it says is you can find out the energy of a photon based on its frequency. So what does that mean? Blue visible light has a higher frequency than red visible light. So blue photons carry more energy than red photons. Okay? Now, normally, when things travel faster, they carry more kinetic energy. But because light is not a conventional particle, we're going to ignore the 1/2 mv² of light waves. We're going to pretend they are masses. Is that clear? So all their energy, all we care about, we're talking about an energy of a photon or energy of a wave, is its frequency. High frequency, high energy, low frequency, low energy. All right, how are we doing? Okay, two points we need to catch. Visible light is a tiny, tiny slice of what's called the continuous spectrum. So this is the electromagnetic spectrum, the whole thing. There's a tiny slice of the spectrum we call the visible spectrum. It's around 10 to the 14, 10 to the 15th waves per second or per second. So we're talking about things that are in so things that are 10 to the -7 meters-ish. So 10 to the 14th, 10 to the 15th hertz in frequency. That's visible light. Energy or waves that are slightly higher in energy than what we can see are ultraviolet, literally above violet. So we got Roy G. Biv and then ultraviolet. And waves that are slightly lower than we can see, lower in energy, are infrared. So there we go. Infrared, ultraviolet. Above ultraviolet, we have X-rays and gamma rays. Below infrared, we got microwaves, radio waves, and so on. Okay. If you're with me so far, give me a thumbs up. And hopefully this PowerPoint is uploaded if you need to refer back to it later. Okay, so we're going to talk briefly about what happens when light slows down. But again, index of refraction, what it actually does is the realm of optics, which for some reason was removed from our curriculum. So it's an optional topic, and we probably aren't going to get to it. So when light travels through space or through air, it travels at 3 × 10 to the 8th meters per second. But the moment the light comes through the window, notice that the window is mostly solid. Okay, light doesn't actually travel through the material, like visibly just pass through it. It actually has to be absorbed by a molecule, handed to the next 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 molecule, and then burped out again. So when light travels through materials, it slows down. The fastest light is going through a vacuum where there's no material for it to get in the way. But when it travels through glass or plastic or anything, it slows down. So here I got my window, it's like zing, zing, zing. So it goes really fast, has to go through the material, has to slow down the material, and then keep going through. So, there you go. And then how much it slows down is given a number called the index of refraction. So if it slows down to 1 point, or it starts at 3, so this is 3. If it slows down to 2, the index of refraction is 1.5, 3/2. If it slows down to 1 × 10 to the 8th meters per second, it has an index of refraction of 3. We don't really have any naturally occurring materials that do that. You can force the issue.
So wait, what does Celsius represent in this? I mean, the Z?
Say again?
What does the C represent?
Speed of light. E = mc². C, speed of light.
You are correct.
Yeah. So C is the speed of light. 3 × 10 to the 8th meters per second. So the ratio of how fast light is in a material to how fast light is in space is our index of refraction. So air has an index of refraction of effectively 1 because we're going 3 × 10 to the 8th meters per second, 3 × 10 to the 8th meters per second. Diamond has a monster index of refraction of 2.4 × 10 to the, or 2.4. So it's 3 divided by 2.4 is how fast it's going. 1.4 × 10 to the 8th meters per second.
Higher or low?
Okay. So again, this you need to know, but what this does in lenses and mirrors is the realm of optics, and we're probably not going to get to it. All right, so there's our visible light, little tiny slice. So wavelengths between 7 × 10 to the -7 and 4 × 10 to the -7, right here, those are visible light. Frequencies between 4.3 × 10 to the 14th and 7.5 × 10 to the 14th, that's also visible light. So when our wavelengths are less than 7 × 10 to the -7 or larger than 4 × 10 to the -7, then you have infrared and ultraviolet. When our frequencies are less than 4.3 times to the 14th or more than 7.5 to the get the idea. So a tiny little slice, visible light. Really great video online, linked in Canvas about ultraviolet. Like the guy has these really cool ultraviolet camera and he goes around and looks at ultraviolet things. Like, whoa, it looked like an ultraviolet. All right, questions? Some of you are madly scribbling, so I'm not sure if you're scribbling, but I'll go ahead and let you scribble. Ready to move on?
Yes.
Okay, this is fun. What makes the dots in the screen and on your phone is a mixture of various wavelengths of light. So we have what are called phosphors, tiny little phosphors, like fractions of a millimeter thick, tiny phosphors, and they're electrified. And they might glow green, or they might glow blue, or they might glow red. So if you're really close to this, you see red, blue, and green dots. But if you were like, probably further to the back of the room, this is a giant screen, you would see gray. And this is what you see when your computer mouse is moving around. You see various darkened colors of dots that says, oh, that's a black arrow. So Bear's talking about, let's talk about colors. The three primary colors, sorry elementary teachers, are not red, blue, yellow. They are in fact red, blue, and green. These are the primary colors of light, red, blue, and green, which is why you frequently hear RGB referred to with computer monitors or televisions. It's how much red, how much blue, and how much green you have. And when you put these primary colors, also called additive colors, together, then you get white. Just like in this animation over here. So the primary colors of light are red, blue, and green, RGB. I guess red, green, blue, RGB. Anyway.
RBG.
You put them together, you get white. Now, also kind of a fun fact, when you mix two primary colors together, you get what's called a secondary color. When you mix blue and green together, you get cyan. When you mix green and red together, you get yellow. And when you mix blue and red together, you get magenta. Those are called the subtractive colors, or the secondary colors, but they are also the primary pigments. Because when you remove them from white light, you get their corresponding color. It's kind of crazy. That's why they're called subtractive colors. So magenta, cyan, and yellow are what you buy when you need to put new toner in your printer. Or new ink in your printer. You get a magenta, a cyan, or a yellow. Because when you put magenta, cyan, and yellow together, you get black. If you put yellow and cyan together, you get green. If you put yellow and magenta together, you get red. And if you put cyan and magenta together, you get blue. Kind of crazy. Yeah. So there are these subtractive colors. You put the subtractive colors together, you get black. Put the primary colors together, you get white. Pretty neat. Okay. Questions? So there's a fun little activity that hopefully we can do. I don't know how good our lights are. I haven't used them in 2 or 3 years. They're back there in that big cabinet right in the middle next to the phonograph. And there's a blue light, a green light, and a red light. You can combine them together to make various colors. Okay. Questions so far? No questions? Are you sure? Moving on. Moving on. Okay. So here's the thing. If you watch the video, you learned that when we look at intensity of light waves, what we care about is power divided by area. So as light travels outward, it actually travels in all directions because light travels in 3 dimensions. If you measure it over a single dimension, it follows the inverse square law. Because light energy travels in 3 dimensions, if you measure it over 1 dimension, it will follow the inverse square law, which means as you go out twice as far, it will have 1 over twice squared the intensity. So if at 1 meter, it is 1 block. At 2 meters, it's going to be 4 blocks. 3 meters, it's going to be 9 blocks. So if you're like 1 meter, it was 10 units of intensity. At 2 meters, it's going to be 2.5 units of intensity. And 3 meters, it's going to be 1.1 units of intensity. It falls off with the square of distance. If you double the distance, you fourth the intensity. If you triple the distance, you ninth the intensity. And again, you remember what power is, right? What's power? Talked about power in the case of energy and forces. We talked about power in the case of electricity. What is power? Power, given the unit of watt, is what?
IV.
That is one of the formulas, yes. There is, power does equal current times voltage, but what is power?
Work over time.
Energy divided by time. So yeah, so work is change in energy divided by time. So it's also work divided by time. So power has a unit of joule per second or a watt. So we frequently say power when we did electricity or V equals IR. We frequently use power as a proxy for brightness because it's power over area is intensity or brightness. So when you're talking about power, you're talking about a joule per second, which is again proxy for brightness. So intensity is power over area. It also falls off with the square distance. Now, here's the fun part. You don't really have to do all the crazy math involved because there is circular calculus required, like because you have a sphere, an outward moving sphere. So what you do need to realize is that intensity falls off the square distance. If you're happy with that, I'm happy with that. Okay. Again, that's why I use, that is a varies with. That's a varies with. I'm not using an equal sign because there's other terms involved here. So we're using a varies with, meaning the typical question is, this light source is 35 watts per square meter, 1 meter away. At 2 meters away, it's going to be this much. It's going to be 1/2 squared, or 1/4 of that. Watts per square meter. Okay. So if you go twice as far, it's 1/4 as much, 1/2 squared. All right, if that makes sense to you, give me a thumbs up. I want to make sure we're all good before we move on. Cool. Wow, that all came up at once. No animation on this page. All right, whatever. Okay, so wave movement phenomena, you learned about diffraction in the video. So refraction is wave movement due to speed change. And again, it is the realm of ray optics, which we're not going to go into because it's an optional topic and we're just not going to go into it. Diffraction is the bending of waves. And the animations involved in the videos did a really good treatment of how things diffract, how things bend around things due to wavelets, where the wave can be split into little pieces and wavelets can move around. But I like to think about a wave like a person walking like this way down the hallway. If you walk like this down the hallway, you're gonna hit people and they're gonna cause you to move. So you're gonna hit someone like boom, you're gonna move this way, you hit another person, boom, you're gonna move this way. So you're going to kind of move around them based on your wavelength. If you have a very small wavelength, you can probably go straight down the hallway. The wider your wavelength, the more you're going to get bent around objects. Objects being like freshmen. Bonk, bonk. So when it strikes an object or a surface with holes, it'll basically bend. I'm going to show you. Again, I can't do better than the animations in the videos. They're just really, really good. So please watch your video guides. They're really excellent. Okay, so that's what it boils down to. Refraction is the changing of a direction of a wave based on a change in speed, and diffraction is bending of the wave based on striking different materials. Okay, questions? You're just absorbing and absorbing. Okay. Taking it all in. Okay, so this is called thin slit or small slit diffraction. When a wave comes in and it hits these slits, what happens, imagine this is the slit right here. A wave comes in and it hits the slit, it's going to bend outward towards that end of the slit and outward towards this end of the slit. So as it comes along, hits here, it bends a little bit this way, bends a little bit this way, and that creates now a spherical wave. Well, as spherical waves overlap, you can do it twice. So imagine a straight wave hits here, now it's bending a spherical wave this way, a spherical wave this way. Those wave fronts still have compressions and refractions, although now we're calling them crests and troughs because we're talking about transverse waves. So those crests overlap and the troughs overlap, and where the crests overlap, you get a bright band. And where the troughs overlap, you get a dim band. Wish I could show you. There's so many really cool things, but dealing with this phenomena. But it is the realm of physics AP2, second semester physics AP. So we don't teach that anymore. So you can turn straight waves into curved waves, and again, where the wave fronts overlap, you're going to have bright fringes, and where the troughs or where the troughs overlap, you're going to have very dark fringes. Okay, so there you go. Again, watch the video. I can't in this format do it justice. The videos, the animations and videos do a much better job. Okay, any questions about this stuff? Can you kind of see in your mind's eye how if you had a bunch of circular waves overlapping, they would create these patterns?
Yeah.
It's like imagine two people jumping into a swimming pool at the same time. Their waves are kind of overlapping. All right. Thin film. This is totally cool. Okay, so let's preface this. We learned, when we learned about sound waves, that when wave energy goes into a new media, some of that energy is going to get reflected and some of that energy is going to get transmitted. The bigger the difference in media density, the more will get reflected. Okay, so far so good? But anytime there's a change in, again, the animation, the video does a great job of this. Anytime there's a change in density, for light waves we call it index of refraction of the media, but it's still density. It's just optical density instead of physical, solid, molecular density. So anytime the light goes through a different density, some energy gets reflected and some energy gets absorbed. And the energy that gets reflected works just like sound waves. When sound waves strike a more dense boundary, they come back how? Do you remember? When sound waves strike a more dense boundary, they came back.
They go through and then we're back.
Close. Inverted,
Yeah,
upside down. So when a sound wave strikes a more dense boundary, it comes back inverted. Which is why, if you want your home theater to sound really good, you want soft materials all around your walls. Because your walls are very dense, they're going to cause the sound waves to get all bugged up. You don't want that. You want the sound energy to be absorbed or reflected upright. When sound energy goes to a less dense boundary, it gets reflected upright. Light works exactly the same way. When light goes into a material, some of it gets transmitted and some of it gets reflected. And then the light energy that gets reflected will interfere with light energy that got reflected a while back. Let me walk you through this. Light comes in, hits the top of the thin film. By thin film, we mean like thin material on the orders of micrometers. Soap bubbles, a layer of oil on top of water. Very thin layers of plastic on top of glass. Okay. Light comes in, strikes the top of the thin film. Some of that energy is reflected. Some of that energy gets transmitted, hits the bottom of the thin film, and some gets transmitted. And some just keeps going through the thin film. This is why you can see through a soap bubble, because some of the light will go right through. But some of it is going to get reflected at the front of the bubble. Some of it is going to get reflected at the bottom of the bubble. And then these reflected waves will interfere. Interference, remember, can be constructive or destructive. It's when you take wave energy and you add its magnitude. When you add the amplitudes, you can have constructive interference, positive amplitude plus positive amplitude, or destructive interference, positive amplitude plus negative amplitude. So incoming wave goes, and then the reflected wave, so some of the wave is going to get reflected at the front of the soap bubble, some of the wave is going to get reflected at the back of the soap bubble, and then those two waves are going to overlap and create this crazy stripy rainbow pattern. That's thin film refraction. You don't get a lot of rain here, but you see it a lot in rainy environments because the rain will get under oil. And when it rains, it'll pick up the oil and you'll have like an oil slick on top of a puddle. It's very, very, very common where it rains a lot. You get a little bit of oil. Here, you generally just get mud because the rain picks up the dirt and the dirt gets in the way. But if you're up in anywhere north of the 40th parallel where it rains a whole bunch, you can like drive along the road and you'll see these rainbow patterns because there's a little bit of oil on top of the water puddles. And then soap bubbles. So go home and blow some bubbles. And next time you see bubbles, you're like, oh, so that's where that rainbow pattern comes from. It comes from the constructive and destructive interference of light waves on the thin film. Because some of the light's reflecting at the front of the film, and some of it's reflecting at the back of the film. Then it happens again on the other side of the bubble. So imagine this is a thin film going all the way around. It'll happen again at the back of the bubble. It'll get another rainbow pattern. Okay. How are we doing? Okay. And because of geometry, these two waves always come back parallel. Because of geometry and phenomenon that we're not going to discuss because that's the realm of realities. Okay, polarization. I actually have polarizing filters. I should have given you a while back. But polarizing filters are pretty cool. And again, I can't do this justice. The video does a much better job of it. But the idea is that waves are traveling. Got a whole bunch of polarizing filters. Waves are traveling, and as they travel, they vibrate in all 360 degrees. That GIF up there is actually pretty good. And because of that, which one? The one in the upper right. Okay, right. So because of that, we can actually etch glass at very, very, very small resolutions and create what are called polarizing filters that work like gates. For all intents and purposes, they are gates. There we go. Got a bunch of them. It's like I was going through the material and we got a lot of polarizing filters for some reason. You can take them out of the glass or out of the plastic. You're super careful with them because they are actually extremely expensive. You ever heard of Polaroid? The company Polaroid?
Yeah.
Guess how Polaroid made their money?
Polarization.
By they
Cameras.
not cameras. Polaroid made their money by patenting this process. It's bananas. But that's how they did it. They patented this polarizing process. So if you get a polarizing filter and you put another one on top of it and then turn it, you can actually see what happens when light gets selected in one direction and then that light is not allowed to flow in any other direction.
That's actually
There you go.
makes it darker.
Yeah. So when light goes through the first filter, it is selected out, and only light vibrating in that direction will be allowed to pass through. And then if you try to make light pass through another filter in the opposite direction, it can't pass through.
That's when I like twist it up. Don't figure it out.
Fun fact, you put it on your phone. So now you can take out your phones, put one filter on your phone and then turn it like this. And depending on how your screen is designed, it'll actually change how much you see.
That's so cool.
Front camera then.
No, the actual screen. The actual LCD screen, they are actually created with polarizing light. And like I can turn mine and it goes like yellow, green, blue, yellow, green, blue. Because it, remember, the light that comes through is green, blue, and red. And one of the ways we can trick the material into giving us better resolutions is saying all the blue will vibrate this direction, all the red will vibrate this direction, and all the green will vibrate this direction. So when you put a polarizing filter over your phone, it will filter out certain colors of light.
Oh, that's so cool.
Really?
Pretty
matter
much,
what,
yeah.
it's
I can't. If I turn it, it just becomes completely black.
Oh yeah, so in that case, all the light is polarized the same direction. Yeah, if your screen just basically goes dark, that means all of the RG and V are all polarized in this exact same direction.
That is so.
And you're just selecting them out on your phone. If it changes color, it means individual colors are polarized. Like that's the way this 4K screen is. When I hold it this way, it's blue. Now it's yellow. Now it's blue. Now it's yellow. The yellow comes from the green and the red. So they polarize blue one direction and green and red the other direction. Kind of fun.
Are you happy?
Yeah, Polaroid. Patent that process, make billions of dollars.
I'm so
Oh, good
happy.
for them.
I'm so happy.
I think we're almost done. Almost done.
Okay.
So, questions so far? All right. This next slide is a review from chemistry about Bohr's model, and it kind of like ties a big loop to what we were talking about at the very beginning of the period about light traveling out of atoms. You know what? I think quantum and then it's photoelectric. Yeah, okay, cool. So, review the Bohr model. Okay, so there's the Bohr model. Review the Bohr model. So the Bohr model basically says, happens to me too. That's perfectly fine. You are welcome to make noise in physics. So remember, electrons exist in levels. We talked about this, and a quanta, like I said at the beginning of the period, is a packet of energy of a specific size. By the way, quanta is singular. Quantum is plural. Fun fact. Actually back up. Quanta is multiple, quantum is singular. So data is multiple pieces of data, like multiple. A datum is a single item. So a quantum is a single thing, and then a quanta is a whole bunch of things. So small packets or quanta of a specific size are required for those electrons to jump up and jump back down. It's kind of like being on stairs. You can't be between two stairs. You can be at level 1, level 2, level 3, level 4, but you can't stand in between two stairs. So electrons are in their ground state.
Watch me.
They absorb energy, and they jump up to some other level. We call that the excited state. They're not there for very long, and they come back down to their ground state, and they release energy. Simplification, of course, but it works pretty well.
They go to the United States.
Sometimes. You go from the ground state to the United States to the excited state. In 1932, Carl approved beer directly from the brewery to Nels Bohr for a scientific achievement.
Huh.
I don't know how that would work, but I'm sure it's a pretty great. It's a pretty great thing. Hey, he's a great physicist. Let's just let him drink all the beer he wants.
I mean,
You know, that's
1930s.
that's Denmark, I guess. Do these things. Okay, so that's the quantum model. And the reason this is important, not only because this is how light gets created, I want you to kind of stew about it because we're going to use this idea in the next idea where we're talking about the photoelectric effect and how electrons can get kicked out. So atomic absorption is what we call it when light goes into an atom and gets absorbed into the atom.
I have a mission that did before.
Yeah,
Yes.
I have too, yeah.
This is a, yes, you saw this one from waves. We talked about waves.
That's what I'm saying.
Oh, okay, yeah.
And this whole slide is from chemistry from last year. You're like, remember on the
Yeah,
screen?
this looks very familiar.
It
Remember on the
does.
screen with when you were at home watching TV, or and then every now and then peer over like, hey, Mr. Byers is talking on the screen. Remember that?
For that first like 3/4 I paid attention, and then at the end I kind of gave up.
I don't know.
Fair
I liked it. I liked it whenever you use like that, like YouTuber models, you make yourself a dog.
That was funny, yeah, I like that.
I like your kid in the background.
Yeah,
had
always
any
in his
pants
underwear.
on.
Never had any pants on.
Yeah.
Like, hey, when you're 6, pants are kind of like optional.
They really are. And when you're in the
And when
nursing
you're
home.
46, pants are kind of
God,
optional.
it
when
was
you're
just
an adult.
so funny because
That's the definition of, they say home means Nevada. Like, home means no pants.
Oh, I hope so. I hate pants.
Everybody hates pants.
I don't know what pants at all. That's the only one.
what is
I don't.
Okay, so atomic absorption is what you get when an atom absorbs visible light, causing the electrons to rise in their levels. That's atomic absorption. Atomic emission is what you get when an electron drops in levels, giving off a photon. Okay, so first energy comes in, drives the electron into a higher level, that's atomic absorption. When that electron comes back down and emits light, that's atomic emission. Again, just like chemistry. How big the gap is determines the energy of the photon. And the energy of the photon determines the frequency of the photon. That determines the wavelength of the photon. And then our eyes read that wavelength and say, oh, that's red. Oh, that's blue. Oh yeah, that's a green photon, all right. So the chemicals in our brains, or the chemicals in our eyes, pick up different wavelengths of light, give off signals to our brains like, I got a green photon here. I got a red photon here. I just picked up a bunch of blue photons. So the bigger the gap, the higher energy the photon is, the higher frequency it will be. Big gap, more blue. Small gap, more red. So we do RGB too. We have receptors that pick up greenish light, receptors that pick up bluish light, receptors that pick up reddish light. If you're missing one of those colors, you are colorblind. So colorblind people don't just see brown, they just see less of one color than another. And you might have very, very weak red receptors and everything might look a little bit yellow to you. Yeah.
That's what I was going to say. It's my cousin's colorblind.
Hmm?
And they say they don't really see whatever it is. They don't know what it is, but they say it looks more like a reddish.
Yeah. So, and there's various degrees of color blindness too. So it just means that you are missing certain proteins that are required to pick up certain wavelengths of light. They're not like, I just see black and white. It's like, no, you don't. You can't differentiate between various shades of blue because you are missing that protein that allows you to see very good blues. Okay. Dogs, they're like, dogs are colorblind. They're not actually. Dogs just don't have very good red receptors. So they don't see things that have reds very well. I mean, why would you? You grew up in the Arctic or in the forest. You care about things that are not red. You greens and browns you care about, and whites. Which is okay. And I think that's where we're going to end. The next thing is going to be photoelectric effect, bright line spectra. Okay, we don't end with bright lines.
5-minute warning.
Okay. So just like with sound waves, Alexa, stop. Just like with sound waves, we have frequencies and wavelengths. So if you graph wave energy versus distance, you're going to get a wavelength from crest to crest or from trough to trough. If you graph wave energy versus time, you're going to get period, just like with sound waves. So, and the only fun thing about this fact, we're talking about EM, we're talking about all things traveling at the same speed. All waves travel the same speed. What does that mean? If you're traveling in a car and you turn on your headlights, if you're traveling in a car, traveling at half the speed of light, and you turn on your wavelength, turn on your headlights, do your headlights go 1.5 the speed of light? No, they only go at the speed of light. If you want to know how that works, that's called special relativity. That's a video on Crash Course. You can watch that. So wavelength is proportional to 1 over frequency. In other words, higher frequency, lower wavelength. Proportionality means there's a C right here. Energy is proportional to or varies with frequency. Energy is Planck's constant times frequency, and Planck's constant is 6.63 times the negative 34 joules seconds. All right, so this is a good place to stop. Questions? Okay.
How do you?
Actually,
I like
Go
what
ahead.
the meaning was. What? I
Lights
said I
go
liked it. I'm
faster
joking.
in red light than blue light, but
Oh,
red light has a slower wavelength, or actually a bigger wavelength. Is that at all correlated, or?
I will tell you what I know. I won't say, I will be like, yes, I know everything, because I don't know everything. But I will tell you that as far as I know, chlorophyll is green because red light is absorbed. So chlorophyll is tuned to pick up red light, as far as I know. So that would be my guess, because it can only absorb light in the chemistry that allows it to absorb those chemicals.
Yeah, because I was just thinking, because I was like, blue moves faster, so you would assume that it would grow faster.
Yeah, also fun fact, the sun distributes, so the sun is what's called a black body radiator. It radiates all wavelengths of light, but there's actually a spike in the green. So if somebody says, what color is the sun? Oh, by the way, if somebody says, what color is the sun? What color is the sun?
Yellow, orange.
White. It's white. Ask an astronaut what color the sun is, they're going to tell you it's white because they've seen it. The sun is a white, all stars. Another thing, despite what you learn in earlier classes, all stars are white.
Yep.
They are not of various colors. The only reason we assign colors to them is because it's easier to say a blue dwarf or a red dwarf than 590 Kelvin. But all stars are white. And the reason that our sun looks yellow is because of all the blue light that is removed or scattered in our atmosphere because of water molecules.
So does that mean space, it appears more white?
Uh-huh. Yeah. In fact, if you look at the pictures that our Mars rovers have picked up, there's like red sand and a black horizon. The sky is just black. It's not blue because there's no atmosphere to scatter light. It's just black. And if it looked up, I haven't seen this picture yet, but I'm sure it's out there. If it looked up at the sun would just be a big white blob. Black background, white star. Because there's no atmosphere to filter out colors of light. But yeah, somebody says, what color is the sun? The proper answer is white.
I mean, if it's a child, it's probably not.
It only looks yellowish orange because of all the atmosphere. And if the particles are really big, like smoke, it's going to look red.
Big smoke.
Like those of you who have driven past or driven through a forest fire, the sun looks red because a lot of stuff's getting blocked.
Or even here, we get fires over here.
The
smoke.
Yeah, okay. What kind just happened?
The big smoke. No, like we get the smoke over here from California.
Wait, and Mr. Byers,